Of the unit vectors from rectangular coordinate system to spherical coordinate system. So for the transformation of the unit vectors from rectangular coordinate system into spherical coordinate system, we consider this diagram. We consider two unit vectors of the cylindrical coordinate system. The unit vector a rho, which is a unit vector of the cylindrical coordinate system, and the unit vector az, which is another unit vector of the cylindrical coordinate system. So we consider a rho and az, which are the two unit vectors of the cylindrical coordinate system. And we consider the unit vector ar, which is the unit vector of the spherical coordinate system. And we know that this unit vector makes an angle theta with respect to z axis. So the unit vector ar makes an angle of theta with respect to z axis. We resolve this unit vector into two components. So this unit vector has a component along z axis, which is cos theta az, and this unit vector has a component along the unit vector a rho. So it has a unit vector along the unit vector az, which is cos theta az, and it has the component along the unit vector a rho. So the unit vector ar can be written as ar has been resolved into two components. It has a component along the unit vector a rho, which is sin theta a rho, plus it has a component along the unit vector az, which is cos theta az. We know that a rho is equal to cos phi ax plus sin phi ay. We resolved this unit vector a rho into these two components in the cylindrical coordinate system. So what we do, we put the value of a rho in equation number 55. Let us put the value of a rho in equation number 55. If we put the value of a rho in equation number 55, we obtain equation number 56. So ar will be equal to sin theta cos phi ax plus sin theta sin phi ay plus cos theta az. So you see, this is the unit vector ar, and this unit vector is in terms of ax, ay, and az. You guys can calculate ar dot ax. ar dot ax will be equal to sin theta cos phi. ar dot ax will be equal to sin theta cos phi. Similarly, ar dot ay, you see, ar dot ay will be equal to sin theta sin phi. And finally, ar dot az will be equal to cos theta. So ar dot az will be equal to cos theta. So we have resolved ar into two. We have resolved ar into three components in equation number 56. And we have already considered, you see, these scalar products. you see that AR dot AX results in sine theta cos phi, AR dot AY results in sine theta sine phi, and AR dot AZ results in cos theta. So we have already considered this. We have already considered these dot products. We go ahead. Okay, in this particular diagram, we consider the two unit vectors of the cylindrical coordinate system as well. So we have the unit vector arrow. This is the unit vector arrow, and this is the unit vector minus AZ. So these are the two unit vectors of the cylindrical coordinate system. And we consider two unit vectors of the spherical coordinate system. AR is a unit vector of the spherical coordinate system which makes an angle of theta with respect to z-axis. And then we consider the unit vector a theta, and we know that the angle between AR and a theta will be 90 degree. The angle between AR and a theta will be 90 degree. We know that AR and a theta are normal to each other. So we consider the angle of a theta with respect to minus AZ. So a theta makes an angle of alpha with respect to this unit vector minus AZ, and we resolve a theta into two components. It has a component in the direction of the unit vector minus AZ, which is minus cos alpha AZ, and it has another component in the direction of the unit vector arrow, which is sine alpha arrow. So we have resolved the unit vector a theta into two components. So if you look at equation number 57, in equation number 57, a theta has been resolved into two components. It has a component in the direction of the unit vector arrow, which is sine alpha arrow, and it has a component in the direction of the unit vector minus AZ, which is cos alpha AZ. So a theta has been resolved into two components. Now let us find out this angle alpha. You see, if you look at this particular diagram, we talk about this angle. This total angle will be 180 degree, right? So we have theta plus 90 plus alpha, which is equal to 180 degree, right? So if we take the sum of these three angles, theta plus 90 plus alpha, the sum of these three angles result in 180 degree, and we can find out alpha from this particular equation. Alpha will be equal to 90 minus theta. So we can find out the value of alpha from figure number 30. So you see, theta plus 90 plus alpha will be equal to 180 degree, and alpha will be equal to 90 minus theta, right? So we put the value of alpha in equation number 57. If we put the value of alpha in equation number 57, we get a theta, and a theta will be equal to cos theta arrow minus sine theta az. And now we put the value of arrow in equation number 58, if we put the value of a rho in equation number 58, we obtain equation number 59. So a theta will be equal to cos theta cos phi ax plus cos theta sin phi ay minus sin theta az. So we have resolved a theta into two components. Now a theta dot ax will be equal to cos theta cos phi. A theta dot ay will be equal to cos theta sin phi, and a theta dot az will be equal to minus sin theta. So let me repeat. A theta dot ax will be equal to cos theta cos phi. A theta dot ay will be equal to cos theta sin phi, and a theta dot az will be equal to minus sin theta. So you guys can find out the scalar product of these unit vectors from equation number 59. And we have already resolved this unit vector a phi into two components in the cylindrical coordinate system. So if you go back to the cylindrical coordinate system, we have already resolved this unit vector a phi into these two components in the cylindrical coordinate system. A phi has two components, minus sin phi ax plus cos phi ay, and it has no component along the axis, so we have plus 0 az. So you see, if you consider the scalar product of a phi and ax, so a phi dot ax results in minus sin phi, a phi dot ay results in cos phi, and a phi dot az results in 0. So we can develop the table for the scalar product of these unit vectors as well. So a theta dot ax is cos theta cos phi. We have already discussed, you see, the scalar product of these unit vectors in the previous slide. A theta dot ay is cos theta sin phi. A theta dot az is minus sin theta. So let us consider equation number 56. We consider equation number 56. Equation number 59 and equation number 60. So we consider equation number 56, equation number 59 and equation number 60, and we write down all these three equations in the matrices format. So these three equations in the matrices format are given over here. So in the matrix, on the left hand side we have the unit vector AR, unit vector A theta, and the unit vector A phi. Then in the transformation matrix we have sin theta cos phi, sin theta sin phi cos theta. Then we have cos theta cos phi, cos theta sin phi minus sin theta, and then we have minus sin phi cos phi 0, and then we have the unit vector ax, the unit vector ay, the unit vector az. So this is how we transform the unit vectors of the rectangular coordinate system into the unit vectors of the spherical coordinate system. Let us consider the transformation of a vector from rectangular coordinate system into spherical coordinate system. So we consider a three-dimensional vector in equation number 61, and this three-dimensional vector is in the rectangular coordinate system. We can represent a three-dimensional vector in the rectangular coordinate system with the help of equation number 61. So vector A will be equal to ax plus ay plus az. So the three components of this vector are known, and these components are in the rectangular coordinate system. We are going to represent the same vector in the spherical coordinate system. So if we want to represent the same vector in the spherical coordinate system, we need to find out the component of this vector in the direction of the unit vector AR, which is represented by AR. We need to find out the component of this vector in the direction of the unit vector A theta, and we need to find out the component of this vector in the direction of the unit vector A phi. So we need to find out these three components. Once these three components are known, we can represent the same vector in the spherical coordinate system. So we know that the component in the direction of the unit vector AR will be equal to A dot AR. So vector A is in the rectangular coordinate system, which has got all the three components in the rectangular coordinate system, and then we have dot, and then we have this unit vector. We simplify the right hand side of equation number 62 with the help of table number 1.6. So we simplify that particular equation with the help of equation number with the help of table number 1.6. We know that AR dot AX is sine theta cos phi, AR dot AY is sine theta sin phi, AR dot AZ is cos theta. This table is very important because this table helps you to transform a vector from the rectangular coordinate system into spherical coordinate system, or a vector from the spherical coordinate system into rectangular coordinate system. So we simplify equation number 62 with the help of that particular table. We know that AX dot AR is sine theta cos phi. We know that AY dot AR is sine theta sin phi, and AR dot AZ is cos theta. So if we simplify the right hand side of equation number 62 with the help of that particular table, we get equation number 63. So we have sine theta cos phi AX plus sine theta sin phi AY plus cos theta AZ. Now we want to calculate the component of this vector in the direction of the unit vector A theta. So the component of this vector in the direction of the unit vector A theta is equal to A dot A theta. So we put the value of A on the right hand side of this particular equation, right? This vector is in the rectangular coordinate system. This vector has got all the three components, the x component, y component, and z component, and then we consider the dot product of this vector with the unit vector A theta. And we simplify the right hand side of equation number 64 with the help of this particular table, table number 1.7. So we have A theta dot AX, which is cos theta cos phi. A theta dot AY results in cos theta sin phi, and A theta dot AZ results in minus sin theta, right? So let us simplify the right hand side of equation number 64 with the help of table number 1.7. So AX dot A theta is equal to cos theta cos phi. AY dot A theta results in cos theta sin phi, and AZ dot A theta results in minus sin theta. So if we simplify the scalar product on the right hand side of equation number 64, we obtain equation number 65. So this is the component of vector A in the direction of the unit vector A theta. So you see there are three components of this component: cos theta cos phi AX plus cos theta sin phi AY minus sin theta AZ. And we already know the phi component of this vector. We derived this equation in the cylindrical coordinate system when we were transforming a vector from the rectangular coordinate system into cylindrical coordinate system. So we have already discussed this equation number 66 in the previous class. So if we know that a phi is equal to minus sin phi ax plus cos phi ay plus 0 az. So what we do, we consider these three equations. We consider equation number 63, equation number 65, and equation number 66, and we write down these three equations in the matrices format. So these three equations are in the matrices format. We have the component of the component of this vector in the direction of the unit vector AR, then the component of this vector in the direction of the unit vector A theta, then the component of this vector in the direction of the unit vector A phi. And here is the transformation matrix. So in the first row we have sin theta cos phi, sin theta sin phi, cos theta. In the second row we have cos theta cos phi, cos theta sin phi minus sin theta. And in the third row we have minus sin phi cos phi 0, and then we have ax, ay, and az. So we can find out the scalar component ar, the scalar component a theta, and the scalar component a phi with the help of these matrices. And once these three components are known, we can write down, you see, the same vector in the spherical coordinate system. This is a three-dimensional vector in the spherical coordinate system. You see, this vector has a component in the direction of the unit vector AR, it has a component in the direction of the unit vector A theta, and it has a component in the direction of the unit vector A phi. So this is how we transform a vector from the rectangular coordinate system into the spherical coordinate system. The transformation of a vector from spherical coordinate system into rectangular coordinate system. So what we do, we consider a three-dimensional vector in the spherical coordinate system. Now you see, a three-dimensional vector in the spherical coordinate system will have three components. It has a component in the direction of the unit vector AR, a component in the direction of the unit vector A theta, and a component in the direction of the unit vector A phi. So if we want to represent the same vector in the in the rectangular coordinate system, we need to find out the x component of this vector, we need to find out the y component of this vector, and we need to find out the z component of this vector. So somehow we need to find out the x, y, and z component of this vector. If we can calculate these three components, then we can represent the same vector in the rectangular coordinate system. So we calculate the x component, and we know that the x component will be equal to a dot ax, right? So we put the value of a on the right hand side, and then we calculate the scalar product of a and the unit vector ax, and we simplify the right hand side of this equation with the help of table number 1.7 and table number 1.6. So you guys need to consider these two tables, and you guys need to simplify the right hand side of this particular equation with the help of these two tables. So ax dot ar results in sin theta cos phi. Ay dot ar results in sin theta sin phi, and az dot ar results in cos theta. Okay, so over here we consider ar dot ax, which is equal to sin theta cos phi, then a theta dot ax, which is equal to cos theta cos phi, and then we consider a phi dot ax, which is minus sine phi. So we simplify the right hand side of the previous equation with the help of table number 1.6 and 1.7. So we get the x component of this vector. The x component of this vector is calculated with the help of equation number 70. We calculate the y component of this vector with the help of this particular equation. We know that a dot ay gives you the y component. So we put the value of a on the right hand side of this equation, and we consider the scalar product of a and the unit vector ay on the right hand side, and we simplify this scalar product with the help of tables number 1.5, 1.6 and 1.7. Okay, so if you simplify the right hand side with the help of tables 1.5, 1.6 and 1.7, we get equation number 72. So ay will be equal to sin theta sin phi ar plus cos theta sin phi a theta plus cos phi a phi. So ay has been resolved into three components. Well, the z component of this vector will be equal to a dot az. So we put the value of a on the right hand side dot az. So we simplify the right hand side of equation number 73 with the help of table number 1.5, 1.6 and 1.7. We know that a r dot az is cos theta, a theta dot az is minus sin theta, and a phi dot az is 0. So we obtain az will be equal to cos theta ar minus sin theta a theta plus 0 a phi. So what we do, we consider these three equations. Let us consider equation number 70, equation number 72 and equation number 74. So we just write down these three equations in the matrices format, and these equations are given in the matrices format over here. We have the scalar component ax, the scalar component ay and the scalar component az. We have the transformation matrix. So in the transformation matrix we have sin theta cos phi, cos theta cos phi minus sin phi. Then we have sin theta sin phi, cos theta sin phi cos phi, and then we have cos theta minus sin theta and 0, and then we have the unit vector then we have the scalar component ar, the scalar component a theta, the scalar component a phi. So what we do, we calculate these three components, I mean the x component, y component and z component of this vector with the help of these matrices. Once these components are known, we can represent the same vector in the cylindrical coordinate system. So you see, we can consider the same vector in the rectangular coordinate system. So this is how we transform a vector from the rectangular coordinate system into spherical coordinate system, and from the spherical coordinate system into rectangular coordinate system. So if we have this vector in the rectangular coordinate system, this vector will have three components. The component in the direction of the unit vector ax, the component in the direction of the unit vector AY and the component in the direction of the unit vector AZ. Right? So this vector is in the rectangular coordinate system. So if you guys want to represent this vector in the spherical coordinate system, you guys will have to calculate the r component of this vector, I mean the component which is in the direction of the unit vector AR, the component which is in the direction of the unit vector A theta, and the component which is in the direction of the unit vector A phi. So if you guys want to transform this vector from the rectangular coordinate system into the spherical coordinate system, you guys will have to calculate AR, A theta, and A phi. Once we calculate these three components, we can represent the same vector in the spherical coordinate system. So how do we calculate AR? We know that AR is basically equal to A dot AR, right? So we put the value of A on the right hand side of this equation, then we simplify the right hand side with the help of table number 1.5, 1.6 and 1.7, and we obtain the scalar component AR of this vector. Then we calculate theta component of this vector. So theta component of this vector will be equal to A dot A theta, right? We put the value of A on the right hand side, and then we simplify the right hand side with the help of table number 1.5, 1.6 and 1.7. The simplification results in this component of the vector. Finally, we compute the phi component of this vector. So the phi component of this vector will be equal to A dot A phi. We put the value of A, and we simplify the scalar product on the right hand side of this equation with the help of table number 1.5, 1.6 and 1.7, and we obtain the equation for the scalar component A phi. Then we write down these three equations in the matrices format, and you see, finally we can write down the same vector in the spherical coordinate system. So the same vector in the spherical coordinate system will be equal to AR into the unit vector AR plus A theta into the unit vector A theta plus A phi into the unit vector A phi, right? So we can write down, you see, the same vector in the spherical coordinate system. Finally, if this vector is in the spherical coordinate system, you see this vector is in the spherical coordinate system. So if we consider this vector in the spherical coordinate system, we have to calculate, if we want to transform this vector from the spherical coordinate system into rectangular coordinate system, we will have to calculate the x component of this vector, the y component of this vector, and the z component of this vector. So we have to calculate the x component, the y component, and the z component of this vector. And you know how to calculate the x component. We know that the x component of this vector will be equal to vector A dot Ax. So vector A dot Ax will give you the x component. Similarly, the y component the y component will be equal to a dot ay, and similarly the z component of this vector will be equal to a dot az, right? So we calculate, you see, these three components, then we write down these three equations in the matrices format, and we can write down the same vector in the rectangular coordinate system. So this is how we transform a vector from the rectangular coordinate system into a spherical coordinate system, and a vector from the rectangular coordinate system into spherical coordinate system, right? Thank you.